Welcome back for this final session of our program on harmonic mass forms and mock modular forms. We have two very interesting talks lined up today for this session. I'll hand it over to the session chair, Professor Siddhi Pathak, to continue the proceedings.
Thank you very much. Once again, good afternoon and welcome to the last session of this meeting. It is my pleasure and singular honor, pun not intended, to introduce once again Professor M. Ramamurthy. Professor M. Ramamurthy received his PhD in 1980 from MIT under the supervision of Harold Stark and Dorian Goldfield. He was then in the faculty at McGill University in Canada, and after which he is currently at Queen's University in Canada, where he holds the Queen's Research Chair and A.V. Douglas Distinguished University Professor. He is also a Fellow of the Royal Society of Canada, Fields Institute, Indian National Science Academy, American Math Society, and Canadian Math Society. He is the recipient of several prizes, and the most recent one of which is the CRM Fields PIMS Prize. He has written more than 300 research papers and 15 very helpful books, as most of us know, and many of us have benefited a lot from these books. He has supervised more than 25 doctoral students, out of which I'm happy to say that I'm one, 50 master students and 50 postdoctoral fellows. Something that may not be very well known is that he's also a recipient of the Queen's Graduate Supervision Awards, Graduate Student Supervision Award, which is given for extensive contribution to graduate student supervision. So with that, I'd like to welcome you, sir. And we are very excited to hear from you about the partition function revisited.
Thank you very much, Siddhi. Thank you to the organizers for inviting me to speak. It's always a pleasure to be here with friends and colleagues and share good conversation and good food. So the partition function, of course, has a long and venerable history. Perhaps the first person to have studied it in a serious sort of way is Euler back in the 18th century. So let's first, this was defined already, P of n is the number of ways of writing n as a sum of non-negative numbers, lambda i's, with lambda 1 bigger than or equal to lambda 2, bigger than or equal to dot, 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 bigger than or equal to lambda k. So we look at this function. This function has a generating function that Euler had noticed. The simple observation that every partition, let's call this lambda. Lambda would be this tuple. And we'll use this notation lambda dash n to indicate lambda as a partition of n. And the observation that Euler had made in this context of the partition function is kind of analogous to the observation that Euler had made in the context of the Riemann zeta function. He had noticed that the unique factorization property of the natural numbers into products of primes affords a product decomposition of a series, summation 1 over n to the s being given as an Euler product. A similar phenomenon exists here because taken for each partition, we can enumerate how many times 1 occurs, how many times 2 occurs, and how many times 3 occurs, and so on and so forth. So to each partition, we can associate uniquely in this fashion a tuple or representation. This is not to be thought of as a number. It's just a notation in which we encode how many times 1 is appearing, 2 is appearing, and so on and so forth. So with this observation in mind, immediately you find that the generating function of the partition function can be written as a product k going from 1 to infinity, 1 minus t to the k inverse. Because each factor, 1 minus t inverse, counts how often 1 is being used, 1 minus t squared inverse counts how often 2 is being used, and so on and so forth. It's pretty clear. So this is again a kind of consequence of an Euler product observation. So it's not unfair to call this some sort of Euler product decomposition of the partition generating function. And using this, Euler had proved many wonderful things. One of them is his famous pentagonal number formula. So in 1750, Euler had shown that product 1 minus t to the n going from 1 to infinity, can be actually written as a sum with pentagonal numbers. This turns out to be minus 1 to the n, t to the n, 3n plus 1 over 2, n is going from minus infinity to infinity. So the inverse of this particular series is actually this series. So this gives us, so if you multiply the two together, you get 1. And therefore, this gives a nice recurrence relation for the partition function. And that is essentially that minus 1 to the k, p of n minus k times 3k minus 1 over 2 equals 0. Which, of course, when the argument of the partition function is negative, this is to be counted as 0. So this is really a finite sum, and the sum is supported for all values of k, 3k minus 1 over 2 has to be less than or equal to n. In other words, the number of summands in this recurrence is roughly of the order of square root of n, right? So you can compute p of n very quickly. And this is what was one of the favorite techniques of Major McMahon, who was doing a lot of computationals with the partition function. Now, the partition function is important in other parts of mathematics. Let me just say to the importance of P of n. It emanates from what are called, already alluded to in previous lectures, Young diagrams. These Young diagrams are a convenient way of visualizing the partition. So if I have a partition of n, then I can write down squares, unit squares. Let's say lambda 1 such squares, lambda 2 such squares. Sorry, this should be like this. Lambda 2 such squares, and so on and so forth. You can visualize the partition in this so-called Young diagram. And it's convenient because there are two ways of looking at this diagram. And as was mentioned in earlier talks, this diagram is a convenient way of discovering new combinatorial identities for the partition function. And the interesting thing is the partition function is the number of irreducible representations of the symmetric group Sn. And not only is it the number of irreducible representations of Sn, it then stands to reason that given a partition, can I construct explicitly the irreducible representation? And the idea is that using this Young diagram here, you can explicitly construct Young diagrams, give rise to explicit construction of the irreducible representations. For those of you who are familiar with automorphic forms, the constructions of the L functions attached to irreducible automorphic representations also rely on the symmetric group and how you decompose the Borel subgroup using a partition. So again, the partition function appears in the representation theory of GLN as well. So this is a very important thing, and given the importance, it's rather puzzling that the asymptotic behavior of P of n was not studied until as late as Hardy and Ramanujan, 1916. So 1918 to be precise. So that's the first time somebody had looked at the asymptotic behavior. So it's surprising. So number 3, asymptotic behavior of P of n is in this landmark paper of Hardy and Ramanujan, 1918. Where they proved the famous formula P of n is asymptotic to 1 over 4 root 3 times n e to the pi square root 2n over 3 as n tends to infinity. So this is their famous paper in which they introduced the circle method. Now, interestingly, the history is such that papers are not necessarily important for what they prove, but papers are important more for the methods they introduce, which can be used to solve other problems. And this particular paper is a case in point. So what I'd like to do in this talk is discuss this particular asymptotic and how it was approached. Maybe it's almost a century now. So the first method is, of course, the Hardy-Ramanujan method, circle method, which was already described briefly in Professor Anderson's talk, where the singularities of the reciprocal of this function play into the Cauchy residue formula, and then you see that the singularities occur at the roots of unity, and hence the name circle method, and you analyze that thing and produce the asymptotic formula through a very complicated analysis. So this is very, very complicated, very powerful method, because this method later on generated a whole new field of mathematics called additive number theory. So this method is very useful for solving questions in additive number theory like Goldbach conjecture or twin primes or whatever things you have. So it's a very powerful method, but in my view, it's maybe not the best way to get this asymptotic formula. So this is 1918. The next development on this question, the master of elementary methods, Erdős's elementary method. Elementary in quotation marks, it just means that he's going to just use his bare hands and ignore any theory. And that could go on forever. And it's really ingenious. I will indicate briefly how his new idea, it's surprisingly elementary, but it's not too hard. This is around 1941. It's a paper in the Annals, 1941. And then the next method is Ingham, 1942 or thereabouts. Ingham came up with the Tauberian theorem. So you give me a power series, any power series, as long as I know its behavior in the neighborhood of 0 or something like that, I'll give you the asymptotic formula. So that's basically Ingham's Tauberian theorem, stated incorrectly in the B4 book, by the way, the Brinkman, Folsom, et cetera, et cetera. Page 255, there's a mistake. So in case you're using the theorem, be careful. Some conditions have not been stated. Okay, that's Ingham's method. That's 1942. Then there's another method by, which I will call the harmonic Maass form method. This uses the Bruinier-Ono formula using singular moduli. Connecting P of n. So they discovered this formula connecting P of n with singular moduli. And this explicit formula was then used by myself and Michael Dewar to show that you get the Hardy-Ramanujan asymptotic, so P of n, whatever I wrote there. N, yes, e to the pi 2n over 3. So this is this, you get this formula by analyzing. Now, it's not a total triviality to go from the Bruinier-Ono formula. You have to do a bit of work using theory of binary quadratic forms, but it's not too hard. It was done in a paper, in the proceedings of the AMS, 5 pages, not too bad. Then the thing I'd like to discuss today, maybe with this being a conference on harmonic Maass forms, I will make some comments about that method. But the fifth method, which I also want to talk about today, is a probability method. This is discovered by the Venezuelan mathematician Baez Duarte. Around 1990 or thereabouts. So this is a very clever idea, and I want to talk about that in about 15 minutes or so, and then report on some work that I had done with my Japanese exchange student, who was a student of Kaneko, and she came to spend some time at Queen's, and we had developed the method of Baez Duarte to do other problems as well. So it seems to work neatly. Now, let me just say a few words about Ingham. So, because it'll be useful for some of the youngsters that might be thinking about applying some techniques from analysis to study coefficients of these generating functions. So this is the outline of what I want to say. So the Ingham-Tauberian theorem, which is worth noting, suppose that f of t is summation n going from 0 to infinity, a sub n t to the n, is a power series with non-negative coefficients. And non-negative and increasing coefficients. So this is actually this is not needed. I'm just going to put it in brackets here because if you check the Ingham paper, you actually don't need it. You can get away with it, but let me just put it in for now. Increasing coefficients and radius of convergence equals 1. Then suppose that there are constants A, positive, lambda, alpha, real, such that f of e to the minus t is asymptotic to a to the alpha exponential a over t as t goes to 0. And also that we find some behavior of the function near 0. Also, f of e to the minus z is bounded by mod z to the alpha exponential a over mod z as z goes to 0. This is the condition that's missing in the Brinkman book. So in case you are trying to use this theorem, only this condition is stated. Then the asymptotic formula is immediate. Then a sub n is asymptotic to lambda a to the alpha over 2 plus a quarter divided by 2 root pi n to the alpha over 2 plus 3 over 4 exponential to square root a n. So this is the asymptotic formula, just pops out once these conditions are given. So the question is now to look at the generating function for the partition function and see how we can get this. And in the context of the partition function, we already observed it's essentially the reciprocal of the eta function, and you know how it behaves near 0 in the transformation law. And using that, so application using the transformation law for the eta function, eta of minus 1 over t is equal to t to the half 1 over 8 of t. So this is all I need, actually, this transformation. We can deduce the Hardy-Ramanujan formula from Ingham's theorem. So this allows us to check what these numbers are. And the behavior of the Dedekind eta function in a neighborhood of 0, you have to do that too. And then out pops the formula. That's all it's needed. So I think I've given you some outline of this. Oh, I should have said something about the clever elementary method of Erdős. And this is what's puzzling. He used an identity which he says was discovered in 1931, but I can't believe that was as late as 1931. The identity is very simple. Let me just tell you what it is, what the idea is. So if you go back to the Euler's recurrence relation, you will notice that the partition function is given in terms of these pentagonal numbers, but then there was an oscillatory factor. So that messes up the calculation. So there's no way you can actually have an induction argument. So let me just make a few remarks on two. Starting from so this is summation P of n T of n. Let me call this for f of t for now. So take logs of both sides. Like so. And then differentiate. So let's expand this thing also. I expanded the log function. Differentiate. So n m to the n m minus 1, and then I would get n m. The n's cancel, so it's just an n. So you get something like this. Yes? Pardon me? I can't hear you.
For the inter transformation, do we need the I?
No, I made everything real. Yeah, you're thinking of IZ, so I've made it all real. Yeah, this is bad notation, I know. Eta is a function in the upper half plane, but I'm using it with the real variable. Just put z equal to it in your classical understanding. Okay, thanks. Yeah. Technically, she's right. I should have put an it, but that messes up my notation for the rest of the talk. Because you're only interested in e to the minus t, the behavior at e to the minus t. Therefore, I'm just putting it instead of, yeah, that's what happened. Okay, yeah. All right, so from here, we get immediately the following recursion. N times p of n is summation v p of n minus kv, where kv is less than or equal to n. So this is an interesting recursion. It's, as far as Erdős is concerned, it says he hasn't seen it until a paper in 1931 by Lester Ford in the American Math Monthly. I'm not sure the history of this formula. So you know what he's going to do? He's going to use induction to prove this formula, the Hardy-Ramanujan asymptotic. So now that he knows what it should look like, he does a very clever induction argument. For the first step is basically he establishes that Pn is less than some constant e to some other constant b root n. Okay, so he's going to start by guessing the behavior and then putting constants in, and then using this particular recursion formula to establish an inequality like that. Very clever. It's a double summation over k and b, exactly. So all, but only finitely many. You see, basically how many products are less than or equal to n, right? I mean, you could rewrite it, but it's not necessary to do that. The other thing is, so, and as far as the lower bound is concerned, he does another clever thing. It's not long, the paper, but it's messy and complicated. But it's ingenious that an elementary method can give rise to this formula. It's ingenious. As I said, Erdős is the master of the elementary method. So I've mentioned this, discussed this, and discussed this. Let me say a few words about my paper with Michael. Yeah, so here's in 2011, Bruinier and Ono discovered the following remarkable formula. So E2 is the usual Eisenstein series. F of Z is equal to 1/2 of E2 of Z minus 2E2 of 2Z minus 3E2 of 3Z plus 6E2 of 6Z divided by eta squared. Now I'm using it in the sense that you have been thinking of. I'm thinking of it as a function on the upper half plane now. Okay. Sorry about that, but have to state it like so. Okay. So you have this form, and this is a form of weight minus 2. Weakly holomorphic modular form. And let R sub k be the usual raising operator. Pardon me? Gamma 06, thank you. It's gamma 06, as he says, on gamma 0, modular form on gamma 06. So usual raising operator, P of Z, put P of Z to be 1/4 pi R sub minus 2 of F of Z. So it's now, this is weight 0. So so we now have, let's see, theorem. 24n minus 1 P of n is equal to this form P, capital P, evaluated at these CM points that we kind of saw in the early morning talks. These are quadratic forms on gamma naught 6. So here we're looking at reduced binary forms. The sum is over reduced binary forms. ABC, this notation was already introduced in the earlier talks. Alpha Q, of course, is equal to minus B plus B squared minus 4C. But in this case, of course, the discriminant is going to be 1 minus 24n. In this case, it's equal to minus B plus 1 minus 24n for 2a in this case. And there's this 6 business is that I have some additional congruence conditions with some additional. Shouldn't be surprising, this formula, but I mean it's surprising in the classically, but after knowing the basics of harmonic Maass forms, it's not surprising that there would be some explicit formula of this shape. And so with this formula in hand, this is a finite sum now, And the question is, can we determine the asymptotic behavior by studying these points and looking at, essentially, this is a very explicit formula which we can write down the Fourier coefficients for, and then you just now have to crank it out very carefully. That's what we did in the paper. The congruence conditions add a certain extra order of complexity, but they can be dealt with without too much trouble. And the analysis is, of course, the careful cusp analysis, how the behavior of the form at the cusps. Okay, more generally, our method has, similar power as the Ingham-Tauberian theorem. More generally, theorem, I can door myself. Let K be even. F the space with the order I infinity. Level 1, by the way, we're doing level 1. Level 1. Suppose that we have such a modular form and write the Fourier expansion like so, then immediately I is actually square root minus 1 here. K being even, of course, this means plus or minus 1. Lambda f of minus m over root 2n, n over m, k over 2 minus a quarter, e to the power 4 pi root nm. So in other words, the pole controls the behavior of this thing. See, what number goes in here is controlled by the pole, along with the constant that goes in front is controlled by the pole. So this is a very general theorem. Our method uses Laplace's method of steepest descent. Later, in joint work with Kannapan Sampath, who was my master's student, we generalized this to study the coefficients of the J function and gave an explicit, used an explicit formula of Kaneko that was similar in spirit to the Bruinier-Ono formula for the J function. Again, an explicit formula in terms of the singular moduli. And using that, we could get the asymptotic formula for the J function as well. So it is really a versatile method. So in the last 20 minutes or so remaining, I want to discuss this probability method, which to me shows more promise, and it's actually fascinating how it just pops out. And frankly, I'm surprised that Erdős didn't think of it, because he's also a master of probability theory. What is it? Yeah, we didn't do it. We left some questions open so that you can do it. No, yeah, I think that paper should be studied. There are more things that can be done with that technique. All right, so let me give you a crash course in probability theory. Before I surprise you with this, the idea of Baez-Duarte. So we have a probability space, we have random variables on the probability space, and we have, so X random variable, on some probability space. If it's a discrete random variable and there's a measure, probability measure, so we have what's called the expectation of the random variable, the expected value of the random variable. We have the variance. So this is called the mean. The variance is the expectation of x, often denoted as sigma squared of x. So sigma would be the square root of that. So it's called the standard deviation. So you have mean, you have variance, you have standard deviation. So these are just words that are hopefully familiar to you. And you have the notion of a probability distribution. Okay, so those are terminologies that I'm going to use. Just wanted to review those terms. So I'm going to write down here column, discrete probabilities, continuous probabilities. Okay, supposing I have a sequence of numbers. Suppose we have a sequence of numbers an. Let f of t be summation non-negative numbers. Suppose let f of t be a sub n to the n, and going from 0 to infinity. Then there's a probability distribution with, then there exists a space, namely with values in the natural numbers. There exists a space, omega, such that with random variable xt, such that the probability of xt equaling n is simply an t to the n over f of t. But all I'm saying is this. Supposing you have a sequence of numbers which are non-negative and add up to 1, then you can envisage a probability distribution with those numbers. In the special case of x to the n over n factorial times e to the minus x, you get Poisson distribution. In the case of n choose k, 1/2 to the k, you get the Bernoulli distribution. So these distributions that you may have read about in your basic probability course are just happen to be the classical examples, but you can take any non-negative sequence of things that add up to 1 and concoct a probability distribution with that density function. And the same applies for, if you have an integral f of x dx equals 1, then you can envisage a probability distribution. F of x is again non-negative. You can envisage a probability space on which the density function is given by f of x. The classic example is, of course, the normal distribution. Normal distribution comes from this probability integral. Right? This probability integral equals 1, and that's the normal distribution. But any non-negative function that integrates to 1 can be viewed from a probabilistic perspective. And I think this is really at the heart of discovery. It's the same old thing, but you're going to look at it another way. To see the extraordinary in the ordinary is the hallmark of genius. So this time, we'll take this approach, and I want to relate it to the normal distribution. So the idea of Bias Duarte, sadly, he died about 10 years ago. By the time I studied his paper and tried to communicate with him, it was 2 years after his death. He died about 10 years ago, so it's a sad story. He died young also. Anyway, the idea here is to consider the partition function. So it goes from 0. Let's call this f of t. And think of the probability distribution xt equals n given by p of n t to the n over f of t. Okay, so envisage a random variable xt such that probability of xt is equal to p of n t to the n. And so the Bias-Duarte theorem is the following. We will say that, I think I misplaced it here. Yeah. The theorem is this. So we will say, I think in my crash course, I forgot to talk about the moment generating function, or the what's often called the characteristic function of a random variable. So let me just review that too. The characteristic function of a random of this particular random. So the expectation of e to the I theta xt, simple exercise, f of e to the I theta t divided by f of t. So under this setting, under this setup, xt has this property. So now you would calculate for this particular random variable the mean function, the variance function, and so on and so forth. The mean function m of t, in this case, turns out to be t f prime of t over f of t. And the variance function turns out to be t m prime of t over m of t. So you see how you can build up very neatly the classical objects that are associated to a random variable by using this particular thing. Now, normally when we, in probability theory, you study functions with mean 0 and variance 1. So to normalize things, we will set z of t to be x of t minus m of t divided by sigma of t. So this has mean 0 and variance 1. Mean 0, variance 1. And so the definition that he gives is the following. We will say f satisfies the strong Gaussian condition if limit t goes to 1, I'm going to assume my radius of convergence is 1, okay? T goes to 1, minus pi sigma of t, pi sigma of t, e, the expectation of this, I already defined z of t there, minus e to the minus 1/2, theta squared d theta equals 0. In other words, if you calculate the characteristic function of the normal distribution, it turns out to be e to the minus 1/2 theta squared. Okay? That's an exercise again. The characteristic function of the normal is this. So what we're trying to say is, suppose that my function f is, at least in the limit, the same as the normal. Suppose. Then you can get your hands on AN. That's what the Bias-Duarte theorem is. The Bias-Duarte theorem says that if you so theorem. If F satisfies the strong Gaussian condition, and then A sub n is asymptotic to f of tau sub n, I'll tell you what these are in a second, root 2 pi, sigma of 1 of tau sub n, tau sub n to the power n, where I think this should have been sigma, where tau sub n is the unique solution of m of tau sub n equals n. Okay, so he makes a couple of points. I've oversimplified his theorem just for the purpose of exposition. The basic calculus tells you that this is an increasing function. And because it's an increasing function, there's going to be a unique value, tau sub n, where that thing hits n. Call that tau sub n. You pick that point, bingo, you've got the formula. That's it. So this is a general theorem, nothing to do with, number theory, just a general theorem. If you have, of course, a strong Gaussian condition. Now, where are you going to get the strong Gaussian condition, and how are you going to apply it for the partition function? Well, that's where the central limit theorem is going to come in. So, how are we going to review this? So, probability theory crash course, that was 1. Probability theory crash course 2. Given a sequence x1, x2, x3, dot, 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 of independent random variables with mean 0 and variance 1. We have x1 plus x2 tends to the normal. This is a normal distribution. In other words, now this I'm oversimplifying the central limit theorem. This is what's called the central limit theorem. You only need independent random variables. You don't need identically distributed. If you were taught that, that was the classical version. But you see, the central limit theorem evolved over a century. And the finest version is what's called the Lyapunov version of central limit theorem. And there's a small technical condition which I'm skipping, which involves the 4th power moments of this thing that you have to deal with. Ignore it for a moment. As long as you have independent random variables, that silly thing is going to the normal. This has got to be the theorem of mathematics. Yes? Yeah, that's one of the part of the conditions, yes. The Lyapunov version fine-tunes the Lindeberg-Feller condition. Yeah, yeah, yeah. So this is the theorem. You just need independence. Yeah. But you need some conditions on the moments, you see. I'm glossing over that, but that's minor issue. So now what you would do is you would write your, so you want to get your hands on the partition function. You want to get your hands on the partition function. You want to apply this theorem, but you need to know whether the strong Gaussian condition holds or not. Is my random variable Gaussian, in the limit at least? And the point is, it is because we have an Euler product. We have an Euler product, and each piece, you have to check what the distribution is for each piece. So each piece, so you can think of whatever random variable you have here as being built up out of the random variables here. So to say it in a much more concise way, the fact that I have a product means that the random variables are independent, and therefore the characteristic function corresponding to the random variable here will be the product of the characteristic functions here. And then the central limit theorem tells me it goes to the normal. Bingo. So and of course you have to check the conditions, but that's basically the idea. And so this paper that I had written now with Karam Ikeda kind of axiomatizes the Baez-Duarte method. And derives some new formulas for some of the classical things that have been done in a harder sort of way, but using probability theory. So I think I'm nearing the end of the time allotted to me. Just to say that the method has greater potential for applications. I mean, she already applied, she's a Kaneko student after all. She applied it to the J function, and that's going to be part of her PhD thesis.
Thank you, sir. Are there any questions?
Yes.
So you say that this last part, you check that this is strongly Gaussian.
Yeah.
You have to kind of check this on the product formula.
Yeah.
Is this how general is this applicable? Like, can you apply this to a lot of? Do you expect to be able to apply this to a lot of other modular forms?
With the product formulas, exactly. Yeah, so the interpretation, every time you have products of things, the psychology for discovery is that they're independent, and therefore that has to kick into a formula. That's the idea. So anytime you have products, yes, it will work. And she did that and even if you didn't have products, you can get the pieces that have products and you're adding them, and you get an asymptotic formula for one, and for the other one, you can still play this game. That's what she played for the J function. Yeah.
Any other questions?
Yes, you have a question? Yes.
Yes. So is there a Dirichlet series
A
analog?
little louder. You have a mic in your hand. Yeah, okay, go ahead.
Is there a Dirichlet series analog of these ideas where the product can be a genuine Euler product?
Yeah, I think so. I think thanks for asking that question. Well, I think it was Atul Dikshit's lecture. He opened up his lecture by quoting Abhyankar saying, "Polynomials and power series, long live polynomials and power series." Well, polynomials and power series are part of generalized Dirichlet series. So everything can be thought of as a generalized Dirichlet series, right? So summation an e to the minus lambda n s. This is the way people thought of Dirichlet series in the olden days. And so if you chose what? I forgot. Lambda n equals minus log x or something, is that? no, minus log n, you get, or log n rather, you get your ordinary Dirichlet series, right? Lambda n equals log n is you get your ordinary Dirichlet series. And if I put e to the minus s to be x and lambda n to be n, you get power series. So if you're talking about Tauberian theorems for power series, they should be included in the there should be a Tauberian theorem for generalized Dirichlet series, which would include both. So coming back to your question, yes, you have the theory of Euler products in the classical sense, and one should interpret that, and I think you kind of go back to your analytic number theory. I mean, look, this whole business of looking at any non-negative sum adding up to 1, or any integral integrating to 1, you now go back to your calculus book and ask yourself, hey, what is the probability distribution? How does this arise? Any non-negative function will give rise to a probability distribution. So you can try and interpret, you're looking at it with the probabilistic eye. So the Euler products of number theory should be looked at that way. And that way, we'll get some new material. Yeah.
So, and in that context, do we know any Dirichlet series analogs of Ingham's Tauberian theorem, for instance?
No.
Okay.
In that context, no.
Okay.
Yeah, so it's a good research project, yeah.
If there are no further questions, let's thank Professor Murty for a wonderful